Welcome to this explainer. Today, we are going to learn how to think exactly like a physicist. And hey, we aren't just going to sit here and memorize a list of dry, static facts. We're actually going to investigate everyday anomalies, challenge our own assumptions, and hopefully uncover some of the hidden rules of the universe. Okay, let's kick things off with two distinct mysteries. First up, why does a boat that's pointed directly across the Nile River always end up landing at a point downstream from its intended destination? And second, why does falling rain leave slanted streaks on the window of a moving bus even when it is falling perfectly straight down outside? I want you to keep these two events in the back of your mind as we go, because as totally different as they seem on the surface, they are both driven by the exact same physical principle. To solve this, we're going to use a highly specific sequence. Now, what's really interesting here is the framework itself: observation, prediction, measurement, and finally, naming. This is actually how real science happens out in the field. We let the physical evidence build the explanation for us, rather than the other way around. So we're going to discover the concept organically first, and then give it its proper scientific name later. So let's jump straight into step 2, prediction. Imagine our boat on the Nile River. The engine power stays perfectly constant and the bow of the boat is pointing straight across to the opposite bank. Now, if the river current suddenly becomes way faster, what happens to the time it takes the boat to actually cross the river? Does the crossing take less time, more time, or exactly the same amount of time? I want you to lock in your mental prediction right now. Seriously, don't worry about being wrong, just make a choice. Okay, to step into the measurement phase, let's scale this massive river down to something you could literally do right at your desk. Imagine you've got a sheet of paper placed right beneath a ruler. You slowly pull the paper toward yourself at a steady speed. That acts as our river current. At the exact same time, you move a pen steadily along the edge of the ruler. That's our boat. The pen is moving straight, the paper is moving straight down, but what kind of line actually gets drawn on the paper? Data from our little scaled-down experiment brilliantly illustrates what happens when we run the numbers. No matter how fast you pull the paper or move the pen, the line drawn on the paper is always a diagonal. And when you measure it, the length of that diagonal path consistently matches the square root of the crossing distance squared plus the pulling distance squared. It is a fundamental geometric reality that these two independent motions combine to create a completely new diagonal path. So the absolutely crucial point here is that we need a new scientific tool to describe this kind of motion. Enter the vector. Velocity isn't just a single number, it's a vector quantity. This simply means it represents both magnitude, which is how fast something is going, and direction, which is where it's actually going. We usually just draw it as an arrow. When you have two velocities happening at the exact same time, like our boat and the river current, they combine head to tail, almost like a giant puzzle. And it's incredibly important to remember that this is a geometric operation, not just ordinary arithmetic. Now for the final step of our learning framework: naming. That single diagonal arrow we just discovered through our paper and pen experiment is officially called the resultant velocity. It's defined as the single velocity vector obtained by combining two or more velocity vectors into one equivalent vector. See, we didn't just blindly memorize a definition, we built it from the ground up. To really master this, we gotta look at the math. You can take any resultant diagonal velocity and break it down into two perpendicular components, just like horizontal and vertical arrows forming a perfect right angle. The horizontal component pointing straight across the river determines how long the crossing takes, while the vertical component that's parallel to the riverbank determines how far downstream we drift. And here is the kicker: they act completely independently, which means, going back to that prediction you made earlier, a faster river current only affects your downstream drift. It doesn't change your crossing time at all. Did you guess right? Let's clear up a massive misconception that trips a lot of people up. If our boat moves through still water at 4.0 meters per second and the river current flows at 3.0 meters per second, our brains naturally just want to add them together. 4 plus 3 equals 7, right? Actually, scratch that. It's completely wrong. Simple arithmetic only works if things are moving along the exact same straight line. Because the boat and the current are perpendicular to each other, we absolutely must use the vector sum utilizing the Pythagorean theorem. And when we actually do that vector math, taking the square root of 4 squared plus 3 squared, we get exactly 5.0 meters per second. If you're sharp with your geometry, you'll immediately recognize this as the classic 3-4-5 right triangle. The actual speed of the boat relative to someone standing on the riverbank is 5 meters per second, not 7. All right, let's pivot for a second and take this vector concept and apply it to our second everyday mystery, the slanted rain on the bus. To truly understand this one, we need to travel all the way back to the year 1632 to a brilliant thought experiment by Galileo Galilei. Galileo imagined a completely closed cabin inside a smoothly moving ship. Inside that cabin, water drips perfectly vertically, fish swim normally in their bowls, butterflies just fly freely. From the inside, without looking out a window, you literally cannot tell if the ship is moving or stationary. Galileo concluded that measurements of motion depend entirely on the observer's frame of reference. Now apply Galileo's logic directly back to our moving bus. To a stationary observer standing on the earth, say, just waiting on the sidewalk, the rain falls perfectly vertically. But to a moving observer looking out from the bus window, the entire frame of reference shifts. The passenger is subconsciously subtracting their vehicle's forward velocity from the rain's vertical velocity. That unique combination of vectors creates a resultant velocity that makes the rain streak diagonally across the glass. It's wild, right? There's actually a very elegant mathematical formula that governs this shift in perspective, known as the relative velocity equation. It basically states that the velocity of object B relative to object A equals the velocity of B minus the velocity of A. Both vectors are drawn from the exact same starting point, and you always subtract the observer's velocity from the object's velocity to find the reality of what that specific observer sees. Let's take these theoretical concepts completely out of the classroom and put them into a high-stakes, real-world application, landing a massive airplane at Borg El Arb Airport during a heavy crosswind. The plane has a forward airspeed of 220 kilometers per hour, but there is a strong, perpendicular crosswind blowing at 40 kilometers per hour. If the pilot just points the nose directly down the runway, that wind, just like the Nile River current, is going to push the aircraft completely sideways. To compensate, the pilot applies what's called a crab angle, pointing the plane roughly 10 degrees directly into the wind. By purposely flying slightly sideways, the resultant velocity lines up perfectly with the runway centerline for a totally safe landing. So we've seen how vectors seamlessly govern boats, planes, and even falling rain, which brings us to our final, completely mind-bending thought for this explainer. Think about Galileo's ship and our bus passenger. How can two careful observers measure completely different velocities for the exact same raindrop without either of them being mathematically or physically wrong? I really want you to chew on that relative velocity puzzle. Understanding that different reference frames yield different, yet equally valid measurements, well, it completely changes how you look at the physical world around you. Thanks for joining me on this explainer, and keep observing the world just like a physicist.